Okay, welcome everybody. This is going to be the second video that we're going to do over Ansys. This video is going to include the full Ansys Fluent conjugate heat transfer analysis. So everything that we do today will just be in Ansys Fluent, and in a later video we will import our results from Ansys Fluent and bring it into a structural model. Just a quick reminder that if you want to access any of the files for this Ansys tutorial, you can go into the Google Drive, go to Tamu Rocket Design, go to Projects, Ragnarok, TCA, and then under the Thrust Chamber folder, there's another folder called Ansys Analysis. And in there we have the RPA data Google spreadsheet, the Ansys Fluent expression dump. We also have both of the CAD files that I used for this model. So we have the Ragnarok Thrust Chamber for the regen channels, and then we have the annulus. We also have an archived version, an archived uneditable version of the Ansys Fluent workspace. And then also we have the configuration file for the RPA analysis. So this has everything that you guys need to rerun the simulations in this video. So to start, we're going to start in a similar spot where we did last time in RPA. Okay, so when we go into RPA, the first thing we want to do is we want to make sure that all of our inputs to RPA are correct. So yes, we're operating at 500 psi. The mixture ratio or oxide to fuel ratio is 2. We're using liquid oxygen and liquid jet A. If we go to the nozzle flow model, we see that our contraction area ratio is 7. Our exit condition is 1/8 atmospheres of pressure. And then our ambient conditions is also 1 atmosphere's pressure. Thrust chamber size, we're sizing for 2,000 pounds of thrust. We have a 1.2 characteristic length, a contraction angle of 50 degrees, and we're using the parabolic contour for our nozzle. And finally, let's go to thermal analysis. Make sure that you're using the Bart's convective heat transfer model. Bart's is the most conservative model that we have, and it is the one that we will use to get our chamber heat fluxes to import into Ansys. Okay, next go down to cooling segments and go to the film coolant slot. Make sure that we are using Jet A as our coolant, that the inlet temperature is 500 Kelvin, because this is the temperature once we go through the regen channels approximately, and the relative mass flow rate is 5%. So this is 15% of our fuel mass flow rate and 5% of our total mass flow rate. Okay, so then we're going to move on to the regenerative cooling section. The thermal conductivity of our material is 300 watts per meter Kelvin. This comes from the GRCOP42 material that we're using. The thickness of the chamber wall to the regen channel is 1.8 millimeters. This varies slightly throughout our CAD model, but for the purpose of the RPA analysis, we're going to set this at what it would be at the throat, which in this case is 1.8 millimeters. The rib height, so these are the height of the regen channels over here, going axially or radially away from the combustion chamber. The thickness or the height of these channels is 2 millimeters at the injector and 2 millimeters at the end of the nozzle, and then it's 1.8 millimeters in the throat. And then the width of the channels, this also needs to match our on-shape geometry. At the injector, the width is 3 millimeters. At the throat, it's 4 millimeters, and right at the throat, it's 1.8 millimeters. The helix angle is 45 degrees for this model, and the number of channels is 45. Make sure that our coolant, in this case, the coolant is RP1. This is because Jet A was not supported as coolant here, but it's fine. Jet A is pretty much the exact same thing. Make sure that your inlet pressure is set to 675. Make sure that the inlet temperature is 300. And the relative mass flow rate, 33% of the mass flow rate relative to the total combustion mass flow rate is going through the regen channels. So because our oxide to fuel ratio is 2.0, right, there is 1 part fuel for every 2 parts oxidizer by mass. And as a result, fuel is 33% of the total mass flow rate. And then make sure that you select coolant flow direction as opposite of hot gas flow direction. So that means that our coolant comes in from the bottom of the thrust chamber and goes up towards the injector. Okay, so after that, we can after we verify all the dimensions in RPA, we can hit run. And then we can come over to thrust chamber size, which is really what we care about. We want to make sure that the dimensions here match the dimensions on shape. And then thermal analysis. Here we can plot the thermal analysis, and we can see how the temperature of our gas side of our wall changes as a function of time. And then we can also see how our coolant changes as a function of time. So you can see that we start at 300 degrees Kelvin and our cooling gets hotter till just below 500 degrees Kelvin. And then we can also see the temperature of the wall and the temperature of the hot gas in our system. So the first thing we're going to want to do with this data is we're going to want to take it and copy it into a new spreadsheet that we can manipulate. So we can go over here to the RPA data spreadsheet. This is a new one that I made called V1.5.2 BARTs. We can paste all of this data here. And then we care about two things. We want the location and we want the total heat flux, but we need to make these in the same units that we're going to use in Ansys. So the location will be in meters, the total heat flux will be in watts per meter cubed. So we can come over here, we can do location. There's 1,000 millimeters in a meter, and then heat flux. Watts per meter squared. And we can come over and so we have heat flux, set the value of that, total heat flux times 1,000, because there are 1,000 watts in a kilowatt, and then we can just autofill. Okay, so this is the data that we're going to use for our heat flux throughout our analysis. So it's just important that we get that now and make our lives easier down the road. Okay, so the next thing that we want to do is we want to come over to the Ragnarok parametric model. We want to make sure that our dimensions in RPA match our dimensions in Onshape. So we can come over here to the variable studio. Sometimes you have to press refresh on the variable studio to get it to update the values correctly. So here we can see that all the values from Onshape match RPA perfectly. And then let's make sure that the regen channels also match. So this is the width and height at the nozzle, so 2 millimeters by 4 millimeters. That corresponds to 2 millimeters by 4 millimeters, so that corresponds to HC2 and A2. And then we have the throat width and height, so that corresponds to HC min and A min, which are both 1.8 millimeters. And then we have the injector width and height, which is 3 millimeters by 2 millimeters. So the height right here is 2 millimeters. The width A1 is 3 millimeters. So we can also see that our helix angle is 45 degrees right here, and that we have 45 channels. So all of our all of our regen channels match the exact dimensions that we have in RPA, and all of our chamber dimensions also match what we have in RPA. Okay, perfect. So now we can go over to the Ragnarok thrust chamber model, and we need to cut this model for the two cases that we're going to run. The first case that we're going to run is going to be just the bottom of the fuel annulus here. We want to see how fluid distributes around the fuel annulus to all the individual regen channels. And the second model that we're going to run is we're going to isolate 5 regen channels and model the fluid flow through those all the way through. So let's get our first model. We can come out down here to the fuel annulus analysis, and we can unsuppress. This is just an extrude that removes pretty much everything except for the bottom of the fuel annulus here. And then we can also hide these curves. There we go, and we can export this. Name it whatever you want and export it as a parasolid. So after that, we can resuppress the fuel annulus analysis, and we can unsuppress the cutout folder. So the cutout folder will make a 5-section cut that we can then also download and bring into Ansys later on. So if you come down here, let's first make sure that all of our curves are hidden. Then let's hide part 1 and hide part 3, and we have just our 5 sections of our regen channels. The next thing that we need to do is we need the inlet to be centered in the middle of the bottom of the fuel annulus so that we can still inject our fuel into this inlet. To do that, we go back to Variable Studios. We're going to go down to the variable called inlet location. I've already made a note that at 45 degrees helix angle, the angle here for the inlet to be where it needs to be is negative 15 degrees, negative 15. This may require some, may require you to try multiple values to get one that works, by the way. And then we can come back to the Ragnarok thrust chamber, and boom. Now our inlet is right where we want it to be in the middle of our annulus for this section cut out. The other thing that you want to watch for is you want to make sure that the regen channels aren't getting cut off through our cut. So if we go and we add a section view and then we scroll down here, we want to look for any cutting. So we can see that we cut through another regen channel or the next regen channel right here. That's okay. What I am worried about is when we cut through one of the regen channels that we're trying to model. So there are a couple ways to fix this. They are a little bit tedious, but we're going to go through them real quickly. So if we go down to the cutout stuff, and then we go to transform 1 and 2, these transform functions radially move the planes that we're cutting along. So if we go to transform 1, we can go to the angle here, and at the end there's a number right here. And we can make this something like 0.2. And if we do that, it will actually lower the angle of the starting regen channel, or the starting regen channel cut. So when we do that, we see that we have more of a cut on this side and less of a cut on this side. So we actually want this one to be smaller or negative. So we can go back into here. We can do 0.2. And we can actually change this to a plus. See what that does. So that fixed it a little bit better, but we can probably do even better than that. We can see that we're no longer cutting off that regen channel at all, which is what we're looking for. Let's edit our section view here. Okay. So now we go all the way down. We don't cut off any of our regen channels. We are close to cutting off that regen channel. But we are able to keep it going all the way down. The other thing that we want to watch out for is we don't want this piece right here to be showing down here, because it'll make our volume extract feature difficult to use. So we're going to have to go back in here. We're going to go transform 2, and then we can edit the last part of this, and we can make this like 0.2. Let's try that. Boom. Okay, so now we don't have any regen channels showing down here. Both of these sides are flat. We want. Okay, so after that, we need to go and make sure that our cuts do not interfere with our flat surfaces right here or right here. Once you're done with that, you can come over here, you can press export. We can name it whatever you want. Okay, so now we have both of our models that we're going to be using in Ansys. And so the next thing that we can do is we can just open up Ansys Workbench. Okay, after Ansys Workbench is open, we're going to go to Fluid Flow Fluent, and we're going to double click on that to add it to our project schematic. After that, we're going to go to Geometry, and we're going to click New Discovery Geometry. Okay, so once Ansys Discovery is open, we can come up to the File menu, and we can insert geometry. Go find your file, your annulus file, and open that. Okay, perfect. Once you import that, we're going to go to Prepare. We're going to go to Volume Extract. And how Volume Extract works is we're going to define the surfaces that enclose a volume, and then we're going to define one of the inside surfaces of the volume. So the surfaces that enclose this volume are the top right here and the inlet to the annulus. And then we're going to click on this button right here, and we're going to select one or any of the inside faces. And then you can click Create. Perfect, and now we see that our volume extract feature has worked, and we have successfully turned the inside of the fuel annulus and the bottom of the regen channels into its own volume. Okay, after you're done with this, we are done with everything that we need to do in Discovery. Go back to your main menu and double click on Mesh. Okay, and once we open up Ansys Mechanical, we can go over to Geometry, and we see that we have our solid here and our fluid volume. The first thing that we're going to want to do is we're going to want to create all of our named selections. So our named selections will allow us to easily select different parts of the system in the future to apply different things to them. So we can right click on our fluid volume, go down to Create Name Selection, and then type fluid volume. We're going to do the same thing for the solid volume. Then we're going to define our inlets and our outlets. So for our inlets, let's come up here to Select Face. And let's select the inlet face. Go down to Create Name Selection, name it Inlet. And then let's select one of our outlet regen channel faces. Right click, go to Create Name Selection, and then type Apply Geometry Items of Same Size. This will apply the name selection to all of these regen channels, even if we only select one. You can name this outlet. And now if we go down to name selections, we have our fluid volume, our solid volume, our inlet, and our outlet. There's one more name selection that we need, and that's our regen channel walls, and this will be used for making our mesh. Okay, you can select 4 sides of one of the regen channels by first clicking on one side, and then rotating with your middle mouse button, and then you can press Control to select all the other sides. And then we're going to right click, go to Create Name Selection, Apply Geometry to Items of Same Size, and then we're going to name this Regen Walls. Perfect. Now if we go down to Regen Walls, we can see that all of our Regen Walls are selected when we clicked on this name selection. And then we also need to add one more name selection to the inside of our chamber that we can put our heat flux load on. So select the inside of your chamber wall, right click, go to Create Name Selection, call this Chamber Wall. Okay, perfect. Now we have all of our name selections done, and we can start our mesh. Before we do that, let's go over to Connections, Contact, and Contact Region, and just make sure that the contact region between the solid and the fluid volumes are correct. After that, we can go down to Mesh, we can go to Insert, we're going to go to Sizing. Instead, for Scoping Method, let's choose Name Selection, and then let's choose Regen Walls as our selected components. Okay, for the element size, we're going to use 0.4 millimeters, so select 0.0004. You can use anywhere from, generally speaking, use anywhere from 0.5 millimeters down to 0.3 millimeters is what I found to be the best element size that balances both computational power required and the fidelity of the simulation. If you go down to 0.3 millimeters, it will take a lot longer, but it will be a better analysis. And then I wouldn't go any higher than 0.5 millimeters because at that point the regen channels get a little bit undermeshed. And then go down and select the growth rate of 1.1. The growth rate controls how finely our mesh changes over time. So it's kind of counterintuitive though. a lower growth rate is technically a better mesh, as in the fineness of the mesh falls off slower, and then a higher growth rate is typically a worse mesh. The fineness of the mesh falls off faster. So after that, we can go over to here, we can right click on mesh, and then we can go generate mesh. And this will take a couple minutes. Okay, so here we can see the complete mesh. We can see that the solid mesh right here is pretty fine all around. This is definitely going to work for us. But let's really isolate the fluid mesh here. We can see that the regen channels are much finer than the outside annulus, and the connection between the regen channels and the outside annulus is also pretty fine. And as we move away from the fine details in the regen channels, the mesh gets less and less fine. This is what that growth rate variable was defining right here. So if you make this growth rate lower, the mesh will stay finer for longer, and if you make the growth rate higher, this finer mesh will dissipate quickly to a less fine mesh. But this mesh looks pretty good, and this should do the trick for us. Okay, so after everything is meshed, we are done in Ansys Mechanical. We can go back to our main screen, click on Mesh, click on Update. Okay, this is probably a good time to save your Ansys project too. Okay, after that we can click on the Setup button, and this is finally going to actually take us into Ansys Fluent. So when you get to the Fluent launcher, make sure that you enable double precision, and then I would recommend using as many cores as your system can handle. After that, you can just press Start. Okay, so right when we come into Fluent, you're going to notice that there are arrows pointing into the inlet and out of the outlet. This is because Ansys has recognized that we named the inlet inlet and the outlet outlet, and it has auto-assigned those features or those parameters to those name selections. There's kind of two ways to work through the workflow in Ansys. One way is to use this top bar here and generally moving from left to right. And the other way is over here on the outline view on the right. Generally speaking, you can start at the top and move your way down. The first thing that we're going to want to do is we're going to want to check our mesh. So we can go over here to check and go perform mesh check. After that's done, we can go over to physics, and on the physics tab has everything that the setup tab has, or most of what the setup tab has, right here, except it's just across. The first thing that we're going to want to do is we're going to make sure that we're doing a pressure-based solver with absolute velocity formulation, and we're solving for a steady state analysis. The next thing that we're going to want to do is we're going to want to take a look at the models. You can either do that up at the models up here or right here. So we're going to want to click energy because we want to use the energy equation, and then we're going to want to make sure that our viscous model is on. For our viscous model, we're going to use the K omega 2 equation model, and you can pretty much leave all of the rest of the parameters in here alone. You know, a lot of these are particular to certain cases or certain models that we don't really need to worry about. You can press OK. And then the next thing we're going to want to do after selecting our models is go to our materials. You'll see that under the fluid and solid, there's already air and aluminum selected, but we're going to want to add some materials. So you can either do that over here by right-clicking on fluid or right-clicking on solid, or you can go up to the materials tab right here and click on it. So for fluid, the fluid that we're going to want to add is Jet A. So come over here to the Fluent database and then scroll all the way down to the J's and find Jet A liquid right here, Jet A fuel liquid. Once you click on that, this menu is going to open up. We're going to want to go down the properties here, and we're going to want to make these properties a function of the temperature. So to do that, like for example density, let's go piecewise polynomial, and this graph will pop up that will show us the density as a function of temperature. Because our temperature, we're expecting to start around 300 Kelvin and end around somewhere between 500 and 550 Kelvin. we can see the density of the fluid changes, by a good 20 to 30%. We want to make sure that all of the properties of the Jet A that we're using change as a function of temperature. So when these profiles pop up, you can just click X, and we're going to go down the list and make sure that all of these are a function of temperature. Some of them won't be. If they aren't, just leave them. After boiling point, none of the rest of them really matter. So don't even bother. After that, you're going to come down here and you're going to click copy. This will copy the material chosen or the fluid chosen and all of the properties that we've set over into our fluids. And then after that, you can press close. So you can see over here in our fluids, Jet A is now right there. And then we also want to add the material that we're using for our actual thrust chamber, the copper material. To do this, select material type solid. Go over here and select the Granta MDS database. And then we're going to go find copper 18200. So material type, go to solid, and then scroll all the way down to the copper alloys. Here we go, copper C18200. This has pretty similar thermal conductivity to what we'll actually be using. These probably won't, the properties of these probably won't vary significantly with temperature. For the purpose of the simulation, this will be fine. Then you can press copy, and then close, and then close. So now we can see that under fluids and solids, we have our Jet A and our copper. Okay, so now we've done models, we've added our materials, now we're going to go to zones. First, we're going to go cell zones, and we're going to select our fluid volume, and then click edit. This is where we're going to specify what fluid we're going to flow through our fluid volume. So material name, let's select jet fuel. And then we can click apply, and we can click close. We're going to do the exact same thing for the solid volume, but we're going to be selecting the material instead of the fluid. So we're going to select our copper alloy, click apply, click close. Then we're going to go to boundaries. There's really only 4 boundaries that we care about. We care about the chamber wall because the heat flux that we're going to put on it, the inlet, the outlet, and then the interior fluid volume, and that's because we're going to specify the roughness. So let's start at the inlet. Click on the inlet, then click edit. Make sure that the inlet type is specified as a velocity inlet. Okay, to find our velocity magnitude, we need to use the mass flow rate equation. So m dot equals rho AV, rho being the density of our Jet A being the area of the inlet, V being the velocity at the inlet. And we're going to rearrange to solve for velocity. So when we do that, velocity equals our mass flow rate of our Jet A divided by the density of our Jet A at the inlet times the area of the inlet. The area of our inlet is just pi times the radius of our inlet squared. So first thing we need to find is we need to find the radius of our inlet. To do that, we can go over to Onshape. We can scroll down to inlet radius I, which is inside radius. We can see that inside radius is 9 millimeters. And then the next thing that we need to know is we need to know what rho is. In this case, rho is going to be 800 kilograms per meter squared, which is the density of Jet A at 300 degrees Kelvin or room temperature. And then our m dot we can find from RPA. So if you go back to RPA to the thrust chamber size tab, you can go down and you can see the mass flow rate of fuel is 1.17 kilograms per second. So then we can come here and we can get out our handy calculator, and we can do 1.17 divided by we do 800 times pi times 0.009 or 9 millimeters squared. And then we see that the velocity of our inlet in meters per second is going to be 5.747 meters per second. So then we can go to velocity magnitude, we do 5.747 meters per second. Okay, perfect. And then on thermal, make sure that our temperature at our inlet is set to 300 Kelvin. We can then click apply, and we can hit close. Next, we're going to go to the outlet. So make sure that the outlet is specified as a pressure outlet. Okay, once we go to pressure outlet, we need to set what the back pressure is. So the back pressure in this case is just going to be slightly above what our previous inlet pressure was. There's not much pressure loss through this because we haven't pushed through the thinnest part of the regen channels yet. So for this number, we're going to use 4.6 E6. So 4.6 megapascals is just 0.05 megapascals less than the inlet pressure, and this should be good enough for our back pressure. And then we're going to see our total backflow temperature. You can just leave this at 300 Kelvin. Click apply, and then click close. Okay, so next we need to make sure that the inside surface roughness is correct for the inside of the regen channels and the inside of the annulus. To do that, we're going to quickly go back to our mechanical section. We're going to click on contact region. And from here, we can see that the target body is the fluid volume and the contact body is the solid volume. So the target body is the body, that surface roughness we want to change. So to do that, we can go into here. We can go up to contact region target. If you double click on this, we can see that wall 21 is the contact region target for the annulus. And then on the regen channels, we can see that it is wall 20. Okay, so we can go and we can click on wall 21. We can click edit. And then we're going to change the sand grain roughness, which will change the internal surface roughness of our fluid volume. We're going to set this to 100 microns, which is 1 to the power of -4. This is roughly the surface roughness that we would expect out of a laser powder bed fusion printed part that is made out of a copper alloy. If this was a stainless steel alloy, it would be roughly 60 microns, or 6e-5, or 6 times 10 to the power of -5. For the purpose of this one, because this is a copper part, we're going to use 1e-4. And we're going to go do the same thing for wall 20. Click on wall 20, click edit, go 1e-4. Okay, so now our surface roughness in the regen channels and in the annulus have been changed to something that we expect out of a laser powder bed fusion printed part. We have specified our outlet pressure, and then we have specified our inlet pressure. The last thing we need to do is change the heat flux on the chamber walls. So over here, thermal conditions, select heat flux, and then over at heat flux, we're going to go find a value that is in the middle of what we want. So the annulus 3D model cuts the model at roughly 91% of the total length of the channel. So we have 50 points here along here, and so if we want the heat flux at roughly 10% of that, we're going to want to move down roughly 5 spots. So 1, 2, 3, 4, 5. And we can come over to total heat flux, and we can see that it's roughly 300 and we can see there's roughly 3,300 kilowatts per meter squared. If we come all the way over here, we can take this number, and this number is probably a little bit high, so we'll use something in the middle as an average. So let's use basically 3 million watts per meter cubed. So we can come back over here and we can go 3e6. So this should be 3,000 kilowatts per meter squared, or 3 million watts per meter squared. And that's the heat flux that we're going to use. And like I said, it's kind of like a right in the middle of the road value. After that, you can click apply, and you can click close. Okay, so now we've set all of the boundary conditions that we care about. So after we get done with defining all of our boundary conditions, we can go down. We don't really care that much about the rest of these. We will touch some of these in the next analysis. Let's go down to methods. This is just so that you guys can see that I'm just using the default methods here. And we're going to go to report definitions. so let's select a flux report. Let's select mass flow rate, and then let's select mass flow rate on our outlet. So we set what the mass flow rate on the inlet is. Setting the mass flow rate on the outlet just allows us to monitor continuity, basically. After that, we can just select OK. And then we're also going to monitor the temperature increase of the fluid on average. So we can go to surface report. We can go to facet average. And then we can select the outlet. And we can select temperature. So this is going to give us the average temperature of the fluid leaving the regen channels. This is just a good value to compute to kind of get an estimate of whatever the fluid is coming out of your system, and to kind of, get see if your model is converging correctly on what you would expect, right? If we see that the fluid coming out of this is like less than 300 degrees, we know something's messed up. If we see if it's something, higher than like 350 degrees, we also know something is probably messed up. So this just allows us to kind of get a good gauge of how accurate our model is, and kind of troubleshoot if something has gone wrong. After that, we can press OK. Then we can press close. Next, we're going to go to residuals. Add another 0 to the continuity residual, and you can pretty much leave everything else the same. Okay, and then all we have to do is we're going to go down to initialization. We're going to click on hybrid initialization, then select initialize. Okay, after hybrid initialization is done, we can go down to run calculation. Let's click check case. No recommendations to make it this time, that's what we're looking for, and let's set the initial number of iterations to 500. After that, you can click calculate, and you can wait for the simulation to complete. Okay, so after the 500 iterations are done, we can go take a look at our scaled residuals. We really want all of our scaled residuals to be less than 0.001. So like you can see here, these residuals are a little bit high, or on the higher side. Really, we'd like this right here, this 2 to be a 3. But pretty much all the other residuals look good except for continuity. So there's a couple ways that we can, reduce this residual. One way is we can try to run for more iterations. So we could run for another 500 iterations, for example. And then another thing that we could do is we could either improve our mesh, which is probably another pretty good way to do it, or relax some of our relaxation factors. And we'll experiment with those a little bit later. If we come over to the mass flow rate section, we can see that our mass flow rate is pretty close to what we'd expect, right? So we would expect negative 1.17 kilograms per second. We have negative 1.15. That's pretty close. And then on the temperature, we can see that we're only getting a roughly 12 degree Kelvin rise in temperature. So that's all pretty reasonable. Then let's go over to the mesh tab, and let's start looking at some of the things that we care about. So under graphics, go to contours, double click on contours, and then let's go to temperature, and let's select all of the walls here. This will allow us to see the temperature on every single surface here, and then we can just press save/display. Okay, so perfect. Now we can actually see what the temperature was over the entire bottom of the fuel annulus. So, we can see that our wall is hot here from our heat flux load, and then as the heat flux distributes out to the regen channels, it gets cooler and cooler. You can see, not a lot of heat flux makes it past the regen channels here. We can also see that, inside of our regen channels, the boundary layer closest to the walls obviously is hotter, and the center section is much cooler. That is something that we would expect to happen here. And this is one of the things that, many things that we're going to want to take screenshots of and report. So when I asked you guys to go, get or do one of these analysis, this is one of the first things that I want to see. The next thing that we could see is we could go to pressure up here. Go to static pressure, and then we can select everything but the walls here. And so the outlet, the inlet, and the interface. Press save, and then if we press save/display, we can see what the static pressure is along the walls. So like for example, here we see that the pressure in the annulus obviously is pretty evenly distributed all around. We do have a slight pressure drop here, which probably means the flow velocity around that curve is pretty high. And then we can see that we have a pressure drop as we're entering the regen channels, and then a pretty steady pressure gradient along the regen channels, which is also what we would expect to see. This is the second thing that we're going to want to look at. This is kind of what's going to tell us what our pressure drop is going to look like through the system. And then there's a bunch of other things in here that we can look at. We can look at turbulence kinetic energy. This is going to show us this is going to be pretty related to the film coefficient. It's going to show us where we have the most turbulence in the regen channels. We can see it's right around the inlets, which is what we would expect here. This one's also important, an important one that we want to look at, because turbulence is a driving factor in the film coefficient or the convective heat transfer coefficient. And so we care about this, and we care about where we have the most turbulence in the system. We can also see that we have some turbulence right around here, right around the inlet, coming around that inlet there. Okay, and then we can go down to wall fluxes, and we can take a look at the wall Func heat transfer coefficient. So this will show us our convective heat transfer coefficient along the inside of the walls of our regen channels. So here, we can see that we have a maximum heat transfer coefficient of, what is that, 13,800 watts per meter squared Kelvin. That's mainly at the inlets to the regen channels, because that's where the most turbulence is going to be. We can see that most of the walls of the annulus has a very, very low heat transfer coefficient or film coefficient. And then obviously after we get through the inlet to the regen channels, the heat transfer coefficient is anywhere from 5,000 to 6,000 watts per meter squared Kelvin, which is actually right where we want it. This was originally sized for the inlet to have a heat transfer coefficient around 5,000, so around 4 to 5,000. So this is a pretty good result. This is a graph that we also really, really care about, because this is directly related to how well our regen channels, transfer heat to the working fluid, to the Jet A in our system. So we're going to want a couple views of this one too. Okay, and the next thing that we're going to want to do is we're going to want to go back to our workbench, and then we're going to want to select results. And this will open up our CFD post-processing. Okay, so once CFD post is open, the first thing that we're going to want to do is we're going to come up to the Streamline, Insert Streamline button. We're going to press OK. And then, so yeah, we want a 3D streamline. We don't want a surface streamline. We want to start from the inlet. So this is where all the streamlines will start, and they'll propagate out from this place. We'll have equally spaced, and we'll put the number of points at, let's do 200 for now. We want to see velocity, and we want the direction to be forward. After that, we can click apply. Okay, and this is going to show us our velocity streamlines throughout the annulus. So we can see that at the velocity inlet, it's pretty uniform, and then it looks like we have a higher velocity going to the left and a slightly lower velocity going to the right. And we can also see where the fluid converges. So it looks like most of the fluid comes all the way around this side, and then only some of it comes from the counterclockwise direction. So this is obviously really, really important to see the distribution of our Jet A through the annulus, and see how our regen channels affects the distribution of this fluid. We can also see the velocity of our fluid increasing as it goes into the regen channels. If we want to get a better view of this, we can see that some regen channels don't have any streamlines in them. One way to fix this is to increase the number of points to around 500. So you can see after we increase the number of points to 500, pretty much every single one of these regen channels has a streamline in it. We can also see that we have an area right over by the inlet of pretty high velocity as the fluid is wrapping around the inside fillet there. So we're going to want several images of the velocity streamlines from several different angles of the fuel annulus. Some areas that we really care about either side of the inlet. We want a top-down view to see how the fluid is distributing along the annulus from both sides. And then we probably want a couple orthogonal views to get images of the regen channels. That pretty much concludes the big ticket items that I want to see in every single report after we do analysis. I'm going to walk you through the rest of the tools in here. So the vector, the insert vector tool. So first, if you want to unselect the streamline, you can just click that, and this allows you to select what you want to be viewing at any given time. And then we can come up here, we can press the vector, insert vector, and then we can define the location that we want to see vectors of. Let's define our fluid volume, and let's define velocity as what we want to see. So we're selecting all domains, location, fluid volume, sampling vertex, factor 1.0. We can adjust this later, and the variable that we want to see is velocity. So now we can see the velocity vectors through the, all of the regen channels. We can see that we do have, some pretty strong velocity spikes right at the inlet, which is kind of what we expect given the inlet geometry being a little bit sharper. Okay, and then putting the factor higher will make the density of the vectors lower. Putting the factor lower will make the density higher. So if we put the factor at 10 and click apply, we'll notice that the density of the arrows reduces significantly. And in some cases, we can actually get a better view of certain areas like the regen channels, for example. Let's set this at 2. We're going to want several images of this one too, specifically focused around the regen channel inlets and around the outside of the annulus. Okay, and the last one that we're going to go over today is volume rendering. So volume rendering lets us see basically cut planes inside of the three-dimensional object that we're looking at. So for domains, you can just select all. For variable, let's start with pressure, although we have a lot of options here. Range will go local, and then let's set the resolution to 50 and the transparency to 0.5, and we can click apply. So here we go. Here we can see that individual planes have been drawn in cross sections along the 3D volume, and then we can see what the pressure is inside of those cross sections. We can also change from pressure to anything else. We can see temperature, for example. Now we can see, so because we had all the domains selected, we can see the temperature through, all of the solid surfaces as well as the fluid surfaces. So, here you can kind of get like a semi-transparent view of the heat fluxes. So here you can get a semi-transparent view of the surface temperature and the temperature inside the solid walls of the annulus.